Hello, in this lecture we'll find out the radius of the big circle. In the drawing we have a big triangle. Inside the big triangle we have two circles and a square. The radius of the small circle is equal to 1 unit. The side length of the square is equal to 3 units, and our mission is to find out the radius of this big circle. Okay, first of all we define the vertex of the triangle here as A. We define this vertex as B, and we define this vertex as C. We define the point of tendency of side BC with the small circle as D. We define the touching point of the square of side BC of the triangle as E. We define the point of tendency of the small circle with the square as F. We define the touching point of side AC of the triangle and the vertex of the square as G. We define the point of tendency of the square with the circle as L. We define the touching point of the square with side BC as N. And we define the point of tendency of tangent BC with the big circle as Q. We define the center of the big circle as P, and we define the center of the small circle as O. We join points O and F together by a straight line. Here point O is the center of the small circle, point F is the point of the circle itself. Therefore OF is the radius of the small circle that is equal to R. The radius is equal to 1, and we have here the radius of the small circle that is drawn to the point of tendency. Therefore, according to rule number 1 that states that a tangent to a circle is perpendicular to the radius drawn to its point of tendency, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. Likewise, we have the radius OB that is drawn to the point of tendency. Therefore, according to rule number 1, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. We know that all the angles inside a square are right angles, so this angle equals to 90 degrees. This angle equals to 90 degrees. This angle equals to 90 degrees. And finally, this angle is also equal to 90 degrees. Here, according to rule number 1, we have the radius PQ that is drawn to the point of tendency. Therefore, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. Okay, and we also have rule number 3 that states that the sum of the angles on one side of a straight line is equal to 180 degrees. So here side BC is the side of a triangle, therefore it is absolutely a straight line. So if we focus on the upper side of the straight line BC at point N, here the sum of the angles on the upper side of BC at point N must be equal to 180 degrees. So which angles we have here? We have this angle is equal to 90 degrees plus the missing angle. In total, they must be equal to 180 degrees according to number 3. Therefore, this angle must be equal to 90 degrees in order to complete the sum of the angles on the upper side of the straight line BC at point N 180 degrees. This angle must be equal to 90 degrees. So, we will focus on the upper side of BC at point E. This angle equals 90 degrees, therefore this angle must be also equal to 90 degrees. Exactly for the same reason that this angle must be equal to 90 degrees. Okay. So actually we found out that inside quadrilateral here, inside quadrilateral FOED, inside the green quadrilateral FOED, we have 1, 2, 3 right angles. Again, 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. The sum of 3 right angles is 270 degrees, therefore in order to complete the sum of the angles here to 360 degrees, this angle must be equal to 90 degrees. So actually we found out that inside quadrilateral FOED we have 4 right angles. And any quadrilateral that has 4 right angles must be at least a rectangle if not a square, so we relate to quadrilateral FOED is a rectangle. Write it down. The green quadrilateral FOED is a rectangle because of the fact that it has 4 right angles. And we know that the opposite sides of a rectangle are equal to each other. That is to say, FO equals to ED. FO equals to ED, but FO is the radius of the circle that is equal to 1, and here from this equation 1 equals to FO equals to ED, we will derive that ED is also equals to 1 unit. ED equals to 1 unit, so we can write here that ED equals to 1 unit. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we get that OD is equal to FE. OD is equal to FE. Okay, OD equals to FE according to the rule that the opposite sides of a rectangle are equal to each other. And here we found out that OD equals to 1, it is the radius of the small circle. So here, from this equation 1 equals to OD equals to FE, we derive that FE is also equals to 1 unit. FE is equal to 1 unit. Okay. We write in the drawing that FE is equal to 1 unit. Therefore, quadrilateral FOED is not a rectangle but a square because all of its sides are equal to each other. So here we know that FE equals to 1 unit. The side left of the square is equal to 3 units. Therefore, GE minus FE minus FE equals to GF. GE is 3, FE is 1, so 3 minus 1 is 2, so GF will be equal to 2 units. Okay. In the next step, I will present to you rule number 2 and we will implement rule number 2 in our drawing. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. Here we have the common external point, point P. From the common external point P, we have two tangents to the circle, tangent PA and tangent PB. And according to rule number 2, they are equal to each other, that is to say PA is equal to PB. We actually can implement rule number 2 in our drawing, because in our drawing, here we will define the point of tendency of tangent AC with the small circle ST. So here we have the common external point G. From the common external point G, we have two tangents to the small circle, tangent GF and tangent GT, and according to rule number 2, they are equal to each other. That is to say, GF is equal to GT, but GF equals to 2, therefore GT must be also equal to 2 because of the fact that they are equal to each other. Likewise, we focus on the common external point C. From the common external point C, we have two tangents to this circle, tangent CD and tangent CT. And according to rule number 2, they are equal to each other. That is to say, CT is equal to CD. So, if CT equals to X, then CD must be also equal to X because of the fact that they are equal to each other. Okay? So, in the next step, we will implement the Pythagoras theorem on the right green triangle GEC. Okay, in the right green triangle GEC, by PT is abbreviation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the green right triangle is GC, therefore the square of the hypotenuse is GC squared. And it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to GE squared plus EC squared. I repeat again, in the right green triangle GEC, according to the Pythagoras theorem, GC squared must be equal to GE squared plus EC squared. What is the value of GC? Here, GC equals to 2 plus x, therefore GC squared will be equal to 2 plus x squared. and plus b equal to ge squared. Ge equals to 2 plus 1, that is 3, therefore ge squared is 3 squared, that is 9, plus ec squared. What is the value of ec? Here, ec equals to 1 plus x, therefore ec squared will be equal to 1 plus x squared. So in total, according to equation number 1, we found out that 2 plus x squared equals to 9 plus 1 plus x squared. We open the brackets on both sides of this equation number 1, and we get that according to equation number 1, 2 plus x squared equals to 2 squared, that is 4, plus x squared plus 2 times 2x, that is 4x, that is equal to 9 plus 1 plus x squared. 1 plus x squared equals to 1 squared, that is 1 plus x squared plus 2x. Here we have x squared on both sides of equation number 1, so x squared will get cancelled. What is left from equation number 1 after we cancel x squared? In this side of the equation we left only with 4 plus 4x. In the other side of the equation we have 9 plus 1, that is 10, plus 2x. Here we subtract 4 from this equation number 1, and we get that according to equation number 1, 4x equals to 10 minus 4 is 6, plus 2x. Here we subtract 2x from this equation number 1, and we get that 4x minus 2x is 2x. And here 2x is equal to 6. Here we divide this equation number 1 by 2, and we get that x equals to 6 over 2, that is 3. So here we found out that x equals to 3 units. Write it down here that x equals to 3 units. And here also x equals to 3 units. Okay. In the next step, we join points O and T together by a straight line. Point O is the center of the circle, point T is the point of the circle itself, therefore OT is the radius of the circle, that is equal to 1. We join points O and C together by a straight line. And we will prove that those two right triangles congruent to each other according to side rule. Here we have the radius that is going to the point of tendency, therefore this angle equals to 90 degrees and this angle equals to 90 degrees. So we prove that those two right triangles congruent to each other according to side rule. So we have here triangle TOC. It's congruent to this triangle ODC. So why those two green right triangles congruent to each other? First of all, TO equals to OD. They are both the radii of the circle, therefore they are equal to each other. So TO equals to OD equals to small r equals to 1. In addition, we have CT equals to CD equals to 3 units according to rule number 2. And finally, we have CO is a common side that belongs to both triangles, so CO equals to itself. It's a common side that belongs to both triangles. So we actually found out that the two small green right triangles converge to each other according to side rule. So I write it down, triangle TOC congruent to triangle ODC according for side roll. And for the fact that those two right triangles can go into each other, we derive that those two angles are equal to each other. According to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore those two corresponding angles must be also equal to each other. So if we define this angle as theta, then this angle must be also equal to theta because of the fact that they are equal to each other. Okay, so we join points T and D together by a straight line. When joining points T and D together by a straight line, we created it triangle TDC. So until what we did until now, from what we did until now, we will conclude that OC is the angle bisector of angle C. Write it down, OC the line segment OC is the angle bisector of this angle C. In triangle TDC. Okay, again, from what we did until now, we can conclude that OC is the angle bisector of angle C in triangle TDC. Why? Because OC or CO bisects angle C into two equal halves. Each half equals to theta. Okay. In the next step, we will define the point of tendency of tangent AC in the big circle as K. We will join points P and K together by a straight line. Point P in the center of the circle, point K is the point of the big circle itself, therefore PK is the radius of the circle that is equal to capital R. We join points C and O together by a straight line. And joining point C and P together by a straight line, we created here two big right triangles. Here the radius PK is drawn to the point of tendency, therefore according to rule number 1, this angle equals to 90 degrees and this angle is also equal to 90 degrees. In the next step, we will prove that those two big right triangles can go into each other according to side rule. So triangle PKC can go into triangle PQC. So all those two triangles can go into each other. First of all, PK equals to PQ. They are both the area of the circle, therefore they are equal to each other. So PK equals to PQ equals to capital R. In addition, if we focus on the common extra point C, from the common extra point C, we have two tangents to the big circle, tangent CK and tangent CQ, and according to rule number 2, they are equal to each other. That is to say, CK equals to CQ. CK equals to CQ according to rule number 2. And finally, CP is a common side that belongs to both angles, so CP equals to itself as a common side that belongs to both angles. So actually prove that the two big triangles can go into each other according to side rule. So I write it down, triangle PKC congruent to triangle PQC according to side rule. And from the fact that those two big triangles can go into each other, we will derive that those two angles are equal to each other. According to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding angles must be also equal to each other. So if we define one angle as theta, then the other angle will be also equal to theta because of the fact that they are equal to each other. In the next step, we will join points P and K together by a straight line. Here we create the triangle QKC. According to what we did until now, we can conclude that PC is also the angle bisector of angle C. It bisects it into two halves, each half equals to theta. So I write it down. PC or CP is the angle bisector of angle C in triangle QKC. I repeat again. CP is the angle bisector of angle C in triangle QKC, as I already mentioned. PC or CP bisects angle C into two halves, each half equals to theta. So angle C has two angle bisectors, OC and CP. Okay. In the next step, we will prove that CO, the angle bisector CO, passes through point P. I'll repeat again, we will prove that angle bisector CO, this angle bisector CO, passes through point P. So I write it down. Our claim is the angle bisector CO passes through point C, through point P, of course. Repeat again on our frame. Our frame is the angle receptor CO passes for point P. We will prove this claim in a negative way. So, in a negative way, let's assume that CO doesn't pass for point P. Okay, so our assumption is that CO doesn't pass for point P. From our assumption, we'll get to a contradiction. Therefore, we'll conclude that our assumption is incorrect, and therefore CO must pass for point P. CO must pass for point P. Okay. So here, if CO doesn't pass for point P, then we will have here angle OCD that is equal to theta. Okay, so we have the first angle, that is angle OCD or DCO. So according to our assumption that CO doesn't pass for point P, we have here angle OCD that is equal to theta, and it is very easy to see from the drawing that CD is part of CB. Again, CD is part of CB. Okay, if CD is part of CB, it means that both CD and CB are located on the same straight line. Okay, why? Because CD is part of CB. So I write it down. So here you can write down that CD and CB are part are located on the same straight line. They lie on the same straight line, or they are located on the same straight line. In the next step, I will draw angle PCB in a new page. I will draw angle PCB in this page. So we have here angle PCB. So actually this is angle PCB that I copied from the original drawing. Those two angles have one leg that are located on the same straight line. DC and BC, they are both located on the same straight line. What about the second leg of those two angles? The second leg of this angle is OC and the second leg of this angle is PCB. Are they located on the same straight line or not? We check here in the drawing. We have here CO, leg CO and leg CP. According to our assumption, CO doesn't pass through point P. If CO doesn't pass through point P, it means that CO and CP are not located on the same straight line. Otherwise, CO must pass through point P. But because of the fact that CO doesn't pass through point P, it means that CO and CP are not located on the same straight line. Okay, according to our assumption, we can write down that CO and CP, they are not located on the same straight line. Repeat again. Otherwise, if CO and CP are located on the same straight line, then CO must pass through point P. But according to our assumption, CO doesn't pass through point P, therefore CO and CP are not located on the same straight line. So we have, in conclusion, we have here two angles, that one leg of those two angles are located on the same straight line. Here BC and CD are located on the same straight line, while the second leg of those two angles, that is to say PC and OC, are not located on the same straight line. Therefore, we conclude that those two angles are not equal to each other. They are different angles, because when you have one angle that is located on the same straight line, if you have one leg that is located on the same straight line of two angles, then the second leg must be also located on the same straight line in order that the two angles will be equal to each other. But according to our assumption, the second leg doesn't located on the same straight line, therefore those two angles can never be equal to each other. So if this angle is theta, we'll define this angle as alpha, and alpha doesn't equal to theta. So here, in conclusion, we actually found out that angle C has two different angle bisectors. That is to say, CO and CP that bisected into two different halves. Okay, angle C has two different angle bisectors, that is to say CO and CP, that bisected into two different halves. While the angle bisector CO bisect angle C into two halves that are theta and theta, the angle bisector CP bisects the same angle C, into different halves that are alpha and alpha. And it is impossible. Why? It is impossible because if angle C equals to 30 degrees, if angle C equals to 30 degrees, then any angle bisector will bisect angle C into two halves that are 15 degrees and 15 degrees only, and not to any other two halves. But here, according to our conclusion, angle bisector angle C will be bisected in two different halves. That is impossible. Why? Because angle C can be bisected if for example angle C equals to 30 degrees, it can be bisected only to 15 degrees and 15 degrees only, and not to any other two halves. So therefore, due to the contradiction, that angle C has two different halves that bisect it into two different halves, we will conclude, and this conclusion is due to our assumption that CO doesn't pass for point P. So we will conclude that our assumption that CO doesn't pass for point P is incorrect, wrong, if our assumption is incorrect, then we must conclude that OC indeed passes for point P. Okay. So we finished with the proof. In the next step, we will focus on the green right triangle ODC. In this green triangle, this angle equals to theta, this angle equals to 90 degrees. Therefore, the third angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in the triangle, and especially triangle ODC. Likewise, exactly for the same reason, in the right triangle PQC, this angle equals to theta, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus theta. In the next step, we will prove that the big right triangle PQC is similar to the small right triangle, triangle ODC. I repeat again, we will prove that the big right triangle, triangle PQC, this big right triangle, is similar to the small green right triangle ODC. So, why those right triangles are similar to each other? First of all, those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to each other. So, this angle QPC, is equal to this angle, that is angle COD. Repeat again, angle QPC equals to angle COD, they are both equal to 90 degrees minus theta, therefore they are equal to each other. In addition, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So write it down, triangle PQC, angle PQC, this angle is equal to this angle, that is actually angle ODC. Again, angle PQC equals to angle ODC, they are both equal to 90 degrees, therefore they are equal to each other. And finally, this angle theta, is a common angle that belongs to both triangles, so angle theta equals to itself. You can define angle theta as angle PCQ, and you can define angle theta also as angle OCD. Repeat again. This equation means that angle theta equals to itself. Okay, define angle theta in two different names. It's a common angle that belongs to both triangles. So we actually proved that those two triangles are similar to each other according to angle similarity rule. So I write it down. We actually proved that the big triangle PQC is similar to the small green right triangle ODC according to angle similarity rule. And for the fact that the two right triangles are similar to each other, we conclude that the following relationship exists between their sides. conclude that PQ in the big right triangle over OD in the small green right triangle is equal to QC in the big right triangle over DC in the small green right triangle. I'll repeat again. We conclude that PQ over OD equals to QC over DC. PQ is the radius of the big circle that is equal to capital R. OD is the radius of the small circle that is equal to 1. QC, what is the value of QC? From the drawing, it is very easy to see that QC equals to 3 plus 1, that is 4, and 4 plus 3 is 7, plus Qn. QC equals to 7 plus Qn, therefore we substitute QC by 7 plus Qn over DC. What is the value of DC? DC equals to x, that is equal to 3 units. So we substitute DC by 3. So in conclusion, according to equation number 1, we found out that R equals to 3 plus Qn over 7 plus Qn over 3. We multiply this equation by 3, we get that according to equation number 1, 3R equals to Qn plus 7. Here we subtract 7 from this equation number 1, and we get that according to equation number 1, Qn equals to 3R minus 7. Qn equals to 3R minus 7, so we can write down in the drawing that Qn equals to 3R minus 7. Okay. So here, because of the fact that the length, the side length of the square is 3 units, we examine 3 different possibilities for the radius of the big circle. Okay. The radius of this big circle could be less than 3 units. This is the first possibility. The radius of this big circle could be equal exactly to 3 units. And the radius of this big circle could be greater than 3 units. Okay, so we start with the first possibility, that the radius of this big circle is less than 3 units. Okay, here, according to our assumption, R is smaller than 3 units. So if R is smaller than 3 units, then here we draw a radius that is smaller than 3 units. This is the radius. So the radius is less than 3 units, and the sine length of the square is 3 units. Therefore, the square must be higher than the radius. So here, okay. This is the square. Each side of this square is equal to 3 units. So this is the point of tendency. This is the radius of the circle that is less than 3 units. And we have the radius pt that is drawn to the point of tendency. Therefore, this angle equals to 90 degrees. And this angle equals to 90 degrees according to rule number 1. So here, inside quadrilateral TP, inside quadrilateral TP and Q, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. So quadrilateral TP and Q is 4 right angles. Therefore, quadrilateral TP and Q is a rectangle. Why? Because it has 4 right angles. And we know that the opposite sides of a rectangle are equal to each other. The opposite sides of a rectangle are equal to each other. That is to say, TP is equal to NQ. TP equals to NQ. But here, TP equals to R, it is the radius of the big circle. And from this equation, R equals to TP equals to NQ, we will derive that R is also equals to NQ. R is equal to NQ. But we have already found out that NQ equals to 3R minus 7. So you can write here that NQ equals to 3R minus 7. And from this equation, R equals to NQ equals to 3R minus 7, we will derive that R equals to 3R minus 7. Okay, so here we subtract R from this equation and we get that R minus R is 0, 3R minus R is 2R minus 7. So here we add 7 to this equation and we get that 2R equals to 7. We will divide this equation by 2 and we'll get that R equals to 3 over 2 7 over 2, here r equals to 7 over 2, that is 3.5 units. So we found out that r equals to 3.5 units, but according to our assumption, r is less than 3 units. R cannot be simultaneously less than 3 units and also equal to 3.5 units, so we have a contradiction here, and due to the contradiction we cancel the possibility that R is less than 3 units. So R cannot be less than 3 units. Why? Because we arrived to a contradiction. Okay, so according to the second possibility, is R equals to 3 units exactly. If R equals to 3 units, then we'll draw here a circle with a radius of 3 units. The radius of this circle is equal to 3 units according to our assumption that R equals to 3 units. So here R equals to 3 units. We know that the side length of the square is also equals to 3 units. Therefore, here the radius and the square will be exactly with the same height. This is the point of tendency, therefore, according to rule number 1, this angle equals to 90 degrees. Here, each side of the square is equal to 3 units, so we go 8 here. So actually, inside quadrilateral PLQN, we have 1, 2, 3 right angles. Okay? Again, inside quadrilateral PLQN, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. So inside quadrilateral PLQN, we have 4 right angles. Therefore, we will relate to quadrilateral PLQN as a rectangle, because it has 4 right angles. It's a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, PL is equal to QN. PL equals to QN. Here PL equals to R, of course, it is the radius of the big circle. So we can write down that PL equals to R. And from this equation, R equals to PL equals to QN, we will derive that QN is also equals to R. QN is also equals to R. So from one side, Qn equals to 1. From the other side, we have already found out that Qn equals to 3r minus 7. Okay. And from this equation, r equals to qn equals to 3r minus 7, we will derive that r equals to 3r minus 7. Here we subtract r from this equation, and we will get that 0 equals to 2r minus 7. We will add 7 to this equation, and we will get that 2r equals to 7. We'll divide this equation by 2, and we'll get that r equals to 3.5 units. According to our assumption, r equals to 3. So r cannot simultaneously be equal to 3 and 3.5 units. So due to the contradiction, we will conclude that r cannot be equal to 3 units. So we left only with the second possibility, that r is greater than 3 units. The first possibility, that r is greater than 3 units. So here we will draw a circle with a radius that is greater than 3 units. So this is the radius of this of the big circle that is greater than 3 units. So if the radius of the circle is greater than 3 units, it means that the height of the radius is higher than the height of the square. So here we draw the square here. Again, the height of the radius is higher than the height of the square. From point L, we will go perpendicular on the radius PQ. Again, from point L, we will go perpendicular on the radius PQ. This angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. Inside, we define the touching point of the perpendicular from point L and PQ as T. Inside quadrilateral TLQN, inside quadrilateral TLQN, we have 1, 2, 3 right angles. Again, inside quadrilateral TLQN, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. So quadrilateral TLQN is a rectangle. Quadrilateral TLQN is a rectangle. Because it has 4 right angles. And you know that the opposite sides of a rectangle are equal to each other. That is to say, TQ equals to LN. TQ equals to LN. But LN is one side of the square that is equal to 3 units. And from this equation TQ equals to Ln equals to 3, we will derive that TQ is also equals to 3. TQ equals to 3. TQ equals to 3 units. So what is the value of TP? The value of TP or PT, it is very easy to say from the drawing that PT equals to PQ minus TQ. Again, PT equals to PQ minus TQ. Okay. PQ minus TQ. So PT or TP equals to PQ, that is R, minus TQ, that is 3. So in conclusion, I found out that TQ equals to R minus 3. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we will get that TL is equal to Qn. TL is equal to Qn. Okay, but Qn equals to 3r minus 7, so we can write here that Qn equals to 3r minus 7, and from this equation TL equals to Qn equals to 3r minus 7, we will derive that TL is also equals to 3r minus 7. TL is also equals to 3r minus 7. In the next step, we will join points P and L together by a straight line. Here, point P is the center of the circle. Point L is the point of the circle itself. Therefore, PL is the radius of the circle that is equal to capital R. In the next step, I will copy the right triangle PTL in a new page, and we will implement the Pythagoras theorem on this right triangle PTL. Okay. So this is the right triangle PTL that I copied from the original drawing. So according to the Pythagoras theorem, here by PT is a relation for Pythagoras theorem. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is PT, therefore the square of the hypotenuse is PL, therefore the square of the hypotenuse is PL square, that is equal to PT square plus TL square. Okay. PL is R, therefore PL square is R square, and it is equal to PT square. PT is R minus 3, therefore PT square is R minus 3 square, plus TL square. TL equals to 3R minus 7, therefore TL square will be equal to 3r minus 7 square. In conclusion, we found out that according to equation number 1, r square equals to r minus 3 square plus 3r minus 7 square. Here, we'll open the brackets on this side of equation number 1, and we'll get that according to equation number 1, r square equals to r minus 3 square is r square plus 3 square, that is 9, minus 2r times 3 is minus 6r plus 3r minus 7 square. 3r minus 7 square equals to 3r square, that is 9r square, plus 7 square, that is 49, minus 2 times 3r is minus 6r, and minus 6r times 7 is minus 42r. Here we have r square on both sides of the equation. Number 1, so r square will get cancelled. What is left from equation number 1 after we cancelled r square? In this side of the equation, nothing is left. We have 0, that is equal to 9r square, minus 6r, minus 42r is minus 48r, and 9 plus 49 is 58. So in conclusion, we have the quadratic equation that 9r square minus 40r minus 48r plus 58 equals to 0. And the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. Here a, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula, that x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. Okay. In our specific quadratic equation, the coefficient a equals to 9. The coefficient b equals to minus 48, and the coefficient c equals to 58. And the variable that we are looking for is r, so x equals to r. We'll put the data inside the equation for x, and we find out the value of the values of r because x equals to r. So here r equals to minus b, b equals to minus 48, so minus b is minus 48, that is plus 48, plus minus square root of b squared. B is minus 48, therefore b squared is minus 48 squared, that is 2304. Minus 4 times a is 9, so minus 4 times 9 is minus 36, times c is 58, and minus 36 times 58 is 2088. All divided by 2a. A equals to 9, so 2a is 2 times 9, that is 18. So here we get that r equals to 48 plus minus 2304 minus 2088 is equal to 164 over check it again. It is equal to 216. 2304 minus 2088 equals to 216. Okay. So inside the square root, inside the root we have only 216 over 18. So here r equals to 48 plus minus the square root of 216 is 14.6969 over 18. So here r equals to, we will have two solutions for r. The first solution is r equals to 48 minus 14.6969 over 18. So r equals to 48 minus 14.6969 is 33.3031 over 18, and 33.3031 over 18 is 1.85. So we found out that r equals to 1.85, but we have already found out that r cannot be less than 3 units, and 1.85 is less than 3 units. Therefore, we'll cancel this possibility, and we left only with the second option. The second solution for r is that r equals to 48 plus 14.6969 over 18. So r equals to 48 plus 14.6969 is 62.6969 over 18. It is equal to 3.483 units. Okay, so actually we found out that the radius of this big circle r, it is equal to 3.483 units, and it is absolutely possible because here r is greater than 3 units. The radius of the big circle equals to 3.483 units. We finished with the question. In the next step, I will summarize the lecture. So, in the drawing, we have a big triangle. Inside the big triangle, we have two circles and a square. The radius of the big circle is equal to 1 unit. The radius of the small circle is equal to 1 unit, and the side length of the square is equal to 3 units, and our mission is to find out the radius of the big circle. Okay. Actually, during the question used 3 rules. So I repeat on the 3 rules that we used in order to answer to the question. We have rule number 1, that a tangent to a circle is perpendicular to the radius drawn to its point of tendency. Here we have tangent AB is tangent to this circle at point M. Point M is the point of tendency. We have the radius that is drawn to the point of tendency. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. So if AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle equals to 90 degrees. Okay, then I present to you rule number 2. According to rule number 2, the lengths of two tangents from common external point to a circle are equal. We have the common external point, point P. From the common external point, point P, we have two tangents to the circle, tangent PA and tangent PB. And according to rule number 2, they are equal to each other. That is to say, PA is equal to PB. And then I presented to you rule number 3. According to rule number 3, the sum of the angles on one side of a straight line is equal to 180 degrees. So we have the straight line CD. If you focus on the upper side of the straight line CD at point O, here the sum of the angles must be equal to 180 degrees according to this rule number 3. So which angles we have at the upper side of CD at point O? We have angle alpha and angle beta, therefore alpha plus beta must be equal to 180 degrees. We use those three rules during answering our question. So here, according to those three rules, we arrive to the conclusion that the small quadrilateral is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, FO equals to ED. Here, FO equals to ED. But here, FO equals to 1 unit. It is the radius of the circle, and from this equation 1 equals to FO equals to ED, we derived that ED equals to 1 unit. Likewise, according to all the opposite sides of a rectangle are equal to each other, we concluded that OD is equals to FD. OD equals to FE. This is point F. OD equals to FE. But here OD equals to 1 unit. It is the radius of the circle. So from this equation 1 equals to OD equals to FE, we derive that FE is also equals to 1. So we actually found out that quadrilateral, the small quadrilateral FOED is not a rectangle but a square, because all of the sides are equal to each other. And then you know that all the angles inside the square are right angles, and so here we used rule number 3. We know that BC is one side of triangle ABC, therefore it is absolutely a straight line. So if you focus on the upper side of BC at point E, here the sum of the angles must be equal to 180 degrees. So which angles we have at the upper side of BC at point E? We have this angle is equal to 90 degrees, therefore the missing angle must be equal to 90 degrees in order to complete the sum of the angles to 180 degrees on the upper side of BC at point E. This angle must be equal to 90 degrees. Exactly for the same reason, if you focus on the upper side of BC at point N, this angle equals to 90 degrees, therefore this angle must be also equal to 90 degrees. Then we focus on point G. From the common standpoint point G, we have two tangents to the circle, tangent TG, tangent GT, and tangent GF. And according to rule number 2, they are equal to each other. What is the value of GF? GF equals to 3 minus 1, that is 2. And we know that according to rule number 2, GF equals to GT, and GF equals to 2, therefore GT must be also equal to 2. Then we focus on the common standpoint point C. From the common standpoint point C, we have two tangents to the circle, tangent CT and tangent CD. And according to rule number 2, they are equal to each other. So if CT equals to X, then CD must be also equal to X because of the fact that they are equal to each other according to rule number 2. Then we implemented the Pythagoras theorem on the green right triangle, triangle GCE. On the green right triangle GCE, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, GC square equals to GE square plus EC square. GC square equals to GE square plus EC square. GC, what is the value of GC? GC, it is very easy to see that GC equals to 2 plus X. Therefore, GC square is 2 plus X square. And it is equal to GE square. GE equals to 2 plus 1, that is 3. Therefore, GE square is 3 square, that is 9. Plus EC square. EC equals to X plus 1. Therefore, EC square equals to X plus 1 square. So, in total, we found out that 2 plus X square equals to 9 plus 1 plus X square. We open the brackets on both sides of this equation number 1, and found out that 2 plus x squared equals to 2 squared, that is 4 plus x squared, plus 2 times 2x is 4x, and it is equal to 9, plus 1 plus x squared is 1 plus x squared plus 2x. Here we have x squared on both sides of the equation, so f squared will get cancelled. What is left from equation number 1 after we cancel the x squared? What is left is that in this side of the equation we left only with 4 plus 4x, and the other side of the equation we have 9 plus 1, that is 10, plus 2x. Here we subtracted 4 from this equation number 1, and found out that 4x equals to 10 minus 4 is 6, plus 2x. Here we subtracted 2x from this equation number 1, and found out that 4x minus 2x is 2x, so 2x equals to 6. Here we divided this equation by 2, and we found out that x equals to 6 over 2, that is 3. So here x equals to 3 and x equals to 3. Okay. Then we join points O and T together by a straight line. Point O is the center of the circle, point T is the point of the circle itself. Therefore, OT is the radius of the circle, of the small circle, that is equal to 1 unit. Then we join point C and O together by a straight line, and we prove that those two right green triangles can go into each other according to side rule. I'll explain what I mean. Here, TO equals to OD, they are both the area of the circle, therefore they are equal to each other. In addition, CT equals to CD equals to 3 units according to rule number 2. And finally, CO is the current side that belongs to both triangles, so CO equals to itself. So those two green right triangles can go into each other according to side rule. And from the fact that they can go into each other, we derive that those two angles are equal to each other according to the rule that corresponding angles in right triangles are equal to each other. So if one angle is theta, then the other angle must be also equal to theta. So we actually found out that CO is the angle bisector of angle C in triangle TDC. Repeat again, OC or CO, it doesn't matter, is the angle bisector of angle C in triangle TDC. Why? Because it bisects, CO bisects angle C into two halves, each half equals to theta. Then we join points P and K together by a straight line. Point P is the center of the circle, point K is the point on the big circle itself, therefore PK is the radius of this circle, that is equal to R. Then we join point C and P together by a straight line. In this way we created those two right big triangles, and we proved that those two right big triangles can go into each other according to side rule. I've explained what I mean. Here PK equals to PQ, they are both the area of the circle, therefore they are equal to each other. If you focus on point C, on the current sum point C, we have two tangents to this circle, to the big circle, tangent CK and tangent CQ, and according to rule number 2, they are equal to each other. That is to say, CK equals to CQ. And finally, CP is the current side that belongs to both triangles, so CP equals to itself. So we actually found out that the two big triangles can go into each other according to side rule. Then we join points Q and K together by a straight line. So we can conclude from what we did until now that CP is also the angle bisector of angle C in triangle QKC. Why? Because it bisects angle C into two halves. Each half equals to theta. So actually we found out that angle C is two angle bisector, OC and CP. They are both bisect angle C into two halves, that each half equals to theta. Okay. Then we had a claim that CO passes for point P. Again, CO passes for point C. Repeat the line of K, CO passes for point P. We proved this claim in a negative way. That is to say, we assumed that CO doesn't pass for point P. Okay, our assumption that CO doesn't pass for point P. Here, CO doesn't pass for point P. And due to our assumption, we got to a contradiction, and therefore we must conclude that our assumption is incorrect, wrong. And if our assumption is incorrect, it means that CO is indeed passes for point P, exactly according to our claim. So that is the process of the proof, that CO passes for point P. So here, let's start with the proof. So we have the assumption that CO doesn't pass for point P. If CO doesn't pass for point P, then we will have here two angles. We have angle OCD that is equal to theta. And it is very easy to see from the drawing that CD is part of CB. Again, CD is part of CB. And if CD is part of CB, it means that CD and CB are located on the same straight line. Okay, then I draw the second angle, angle PCB. This is angle PCB. So we have here two angles, that one leg of those two angles are located on the same straight line. What about the second leg of those two angles? The second leg of those two angles is OC in this angle and PC in this angle. So what about them? According to our assumption, CO doesn't pass for point P. If CO doesn't pass for point P, it means that CO and CP are not located on the same straight line. Otherwise, if CO and CP were located on the same straight line, then CO must pass for point P. Otherwise, we must conclude that CO and CP are not located on the same straight line. Okay, there is no other way. Okay, so here, according to our assumption, CO and CP are not located on the same straight line. Why? Because CO doesn't pass for point P. Okay, so therefore, here we have those two angles, that one leg of those two angles are located on the same straight line, while the second leg is not located on the same straight line. So if this is the situation, it means that those two angles must be different angles. The only way those two angles will be equal to each other is if the second leg also will be located on the same straight line. But according to our assumption, the second leg, CP and OC, are not located on the same straight line. Therefore, we must conclude that those two angles are different angles. So we found out that angle C is two different angles that bisect it, that is to say CO and CP, that bisect it in two different halves. While the angle bisector CO bisected into theta and theta, the angle bisector CP bisected into alpha and alpha. And this is not possible. Why? Because if angle C, for example, is equal to 30 degrees, any angle bisector will bisect it to 15 degrees and 15 degrees only, and not to any other angle. But here we found two different halves for angle C. That is impossible. already showed you here. So due to the contradiction, we conclude that our assumption is incorrect, and if our assumption is incorrect, we must conclude that CO indeed passes through point P. Okay, CO passes through point P. In the next step, we focus on triangle COD. This angle equals to theta, this angle equals to 90 degrees, therefore the third angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees. That is the sum of the angles in any triangle. Then we focus on triangle PQC. This angle equals to theta, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus theta, so I will explain it to you here. Okay, so then we prove that triangle PQC is similar to triangle ODC according to angle similarity rule. So why those two triangles? Triangle PQC is similar to triangle ODC. Why those two triangles are similar to each other? First of all, those two angles are equal to each other. They are both equal to 90 degrees minus theta, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, therefore they are equal to each other. And finally, we have angle theta that is a common angle, it belongs to both triangles, so angle theta equals to itself. In conclusion, found out that those two triangles are similar to each other according to angle similarity rule. And from the fact that those two triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that PQ in the big triangle over OD in the small triangle is equal to QC in the big triangle over DC in the small triangle. And repeat again, we conclude that PQ over OD equals to QC over DC. Okay, PQ equals to R, OD equals to 1 unit, it is the radius of the small circle. QC, what is the value of QC? QC equals to 3 plus 1, that is 4, and 4 plus 3 is 7, plus Qn. So you can substitute QC by 7 plus Qn over DC. DC equals to x, that is equal to 3 units, therefore we substitute the DC by 3 units. And in conclusion, we found out that according to equation number 1, R equals to 7 plus Qn over 3. Here we multiply this equation number 1 by 3, and found out that 3R equals to Qn plus 7. We subtracted 7 from this equation number 1, we found out that Qn equals to 3R minus 7. Here, Qn equals to 3R minus 7. And because of the fact that the side depth of the square is equal to 3 units, we will examine 3 different possibilities for the value of R. R could be either less than 3 units, R could be equal to 3 units, or R could be greater than 3 units. So here we have the first possibility, that R is less than 3 units. If R is less than 3 units, if the radius of this circle is less than 3 units, and the side depth of the square is 3 units, it means that the side depth of the square will be higher than the radius. So you can see in the drawing. So here we have this angle equals to 90 degrees according to rule number 1. So inside quadrangle QT, P, T, and Q, we have 1, 2, 3 right angles. Therefore, the fourth angle must be equal to 90 degrees also. So inside quadrangle Q, T, and P, T, and Q, we have 4 right angles. Therefore, quadrangle P, T, and Q is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, TP equals to NQ. But TP equals to R. This is the radius of the circle. And from this equation, RT equals to TP equals to NQ, we derive that R equals to NQ. So from one side, R equals to NQ equals to R. From the other side, we have already found out that NQ equals to 3R minus 7. So from this equation, R equals to NQ equals to 3R minus 7, we derive that R equals to 3R minus 7. Here we subtract r from this equation, and we found out that r minus r is 0 and 3r minus r is 2r, so in conclusion we found out that 0 equals to 2r minus 7. We added 7 to this equation and found out that 2r equals to 7. We divided this equation by 2 and found out that r equals to 7 over 2, that is 3.5 units, but according to our assumption r is less than 3 units. So r cannot be simultaneously less than 3 units and also equals to 3.5 units. So due to the contradiction, we cancel this possibility, that is to say r cannot be less than 3 units. Then examine the second possibility. That r is equal to 3 units exactly. So if r equals to 3 units, the radius of the circle is 3 units and the side length of the square is also 3 units. Therefore, the height of the radius, so the height of the square and the radius are the same height, as you can see in the drawing. So inside quadrangle PLQN, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. Therefore, quadrangle PLQN is a rectangle because it has 4 right angles, and we know that the opposite sides of a rectangle are equal to each other. That is to say, PL equals to QN, but PL equals to R, and from this equation, R equals to PL equals to NQ, we derive that R equals to NQ. From one side, R equals to NQ, from the other side, from one side, QN equals to R, from the other side, QN equals to 3R minus 7. So from this equation, R equals to QN equals to 3R minus 7, we derive that R equals to 3R minus 7. We subtracted r from this equation and found out that 2r minus 7 equals to 0. We added 7 to this equation and found out that 2r equals to 7. We divided this equation by 2 and found out that r equals to 3.5 units. R cannot simultaneously be equal to 3 units and also to be equal to 3.5 units. So due to the contradiction, it cancels the possibility that r equals to 3 units. That is to say, r cannot be equal to 3 units. Then we had the first possibility, that r is greater than 3 units. So if the radius of the circle is greater than 3 units, it means that the square will be shorter than the radius, because the side of the square is 3 units. So here inside quadrangle, so from point L, we draw perpendicular on the radius PQ. Again, from point L, we do perpendicular on the radius PQ. Therefore, this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. So inside quadrangle TLQN, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. So inside quadrangle TLQN, we have 4 right angles. Therefore, quadrangle TLQN is a rectangle. We know that the opposite sides of a rectangle are equal to each other. That is to say, TQ equals to LN. But here Ln equals to 3 units. This is the side length of the square. And for this equation, TQ equals to Ln equals to 3, we derive that TQ is also equals to 3 units. TQ equals to 3 units. Likewise, according to the sum rule that the opposite sides of a rectangle are equal to each other, we get that TL equals to QN. But before that, what is the length of PT? From the drawing, it is very easy to see that PT equals to PQ minus TQ. Again, PT equals to PQ minus TQ. So PQ equals to R, and TQ equals to 3. So in conclusion, we found out that TP equals to R minus 3. TP equals to R minus 3. So according to the sum of the opposite sides of a rectangle are equal to each other, we get that TL equals to QN. But QN equals to 3R minus 7. So from this equation, TL equals to QN equals to 3R minus 7, we will derive that TL is also equals to 3R minus 7. Yeah, TL is also equals to 3R minus 7. In the next step, I copied the right green triangle PTL in a new page, and we implemented the Pythagoras theorem on this right green triangle, triangle PTL. The right green triangle, triangle PTL, here by PT is by Pythagoras theorem. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, PL square equals to PT square plus TL square. PL is R, so PL square is R square. PT is R minus 3, so PT square is R minus 3 square plus TL square. TL is 3R minus 7, so TL square is 3R minus 7 square. We open the brackets on this side of equation number 1. We found out that R square equals to R minus 3 square is R square plus 3 squared, that is 9, minus 2 times R times 3 is minus 6R, plus 3 minus R squared is 3R squared, that is 9R squared, plus 7 squared, that is 49, minus 2 times 3R is minus 6R, times 7 is minus 42R. Here we have R squared on both sides of the equation, so R squared will get cancelled. What is left from equation number 1 after we cancelled R squared? In this side is nothing is left, in the other side we have 9R squared, and minus 6R minus 42R is minus 48R. 9 plus 59 is 58. So in conclusion, we found out that we have the quadratic equation that 9R squared minus 48R plus 58 equals to 0. And the general formula for quadratic equation is ax squared plus bx plus c equals to 0. Here a, b, c are the coefficient of the quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula, that x is equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, a equals to b equals to minus 48, and c equals to 58. We put the data inside the equation and found out that r equals to 48 plus minus square root of b squared. B is minus 48, so b squared is minus 48 squared, that is 2304. Minus 4 times a is 9, minus 4 times 9 is minus 36, and minus 36 times c is 58. So minus 36 times 58 is 2088. So over 2a, a is 9, so 2 times a is 2 times 9, that is 18. So here 2304 minus 2088 is 216. So inside the root we left only with 216. So here r equals to 48 plus minus square root of 216 over 18. The square root of 216 is 14.6969. So in conclusion, we have here two solutions for r. We have r equals to 48 plus minus 14.6969 over 18. The first solution here, r equals to 48 minus 14.6969 over 18. 48 minus 14.6969 is 33.3031. And if we divide it by 18, we'll get 1.85. So according to the first solution, r equals to 1.85. But we have only found out that r cannot be less than 3 units, and 1.85 is less than 3 units. Therefore, we will cancel this solution, and we left only with the second solution, that the radius of the big circle equals to 48 plus 14.6969 over 18. 48 plus 14.6969 is 62.6969, and if we divide it by 18, we get that the radius of the big circle that we are looking for, it is equal to 4.483 units. Here, the radius of this big circle is equal to 3.483 units, that is greater than 3 units, therefore it is absolutely possible because r is greater than 3. According to our analysis, it is absolutely possible. So the radius of this circle, capital R, equals to 3.483 units. Okay? Thank you very much.